Okay, so last time what we were discussing was like simultaneous shifting and scaling. In that, what we were saying is like, if we have all the options that we had discussed individually are there and present in one format, like a times, there is a scaling with the amplitude, then there is a time shift with the time t naught, and then scaling by a factor b in the time domain in the time variable. So if that is the situation, then we saw that there are this is a particular way of doing it. That is, once you amplitude scale, then you scale the time, and then you do the time shifting operation. So what we saw is order is important here. You have to go in this format. Otherwise, when we reverse the situation, like when we did the time shifting followed by time scaling, then whatever we got as an output was not equal to the this factor. This was not equal, and they can become equal until if you have b equal to 1 or the time shifting factor equal to 0. So you can see that order is important if you have something like this, but it's not compulsory that always you have to do a time scaling followed by time shifting. So it's not important. So I will give you one counter example for that, and that is like, if you have something like this. So if you have something like this here, then that particular sequence, if you follow, then this one, if you follow, then the answer will not be correct. So what you see here is, if you want to generate GT, then the best that you can do is, you first of all do the amplitude scaling here. The amplitude scaling will be a times xt, followed by, now somebody's mic is open, I guess. Can you please turn off your mic? Yeah. Okay. So what we have is, you scale the amplitude a, and then now what you are doing, you are time shifting by a factor of t naught. So when you do a time shifting by a factor of t naught, it will become axt minus t naught. And then what you do is, you scale the time by bt. So when you scale the time by bt, it will only affect the variable t here, not this constant value of t naught. So if that is the situation, you will get ax bt minus t naught, which is actually the one which you want to achieve. So here you observe that we are actually doing a time shifting first, followed by scaling. In the earlier situation, we saw that scaling was done followed by time shifting. So now you can see that depending upon the type of situation, depending upon the type of signal, any order will work. So there is no prescribed rule that you have to follow a shifting followed by scaling, and or the other way around. Depending upon the example or depending upon the situation, you have to do these operations. So if you do the other way around, that is, if you scale first followed by shifting, you will get something like this. As you can see, if you scale by bt, then what will happen? It will become ax bt, and then when you do a time shift operation on this, then it will become b of t minus t naught. So actually it is now ax bt minus bt naught, whereas you wanted ax bt minus t naught and not bt naught. So this bt naught is coming extra. So that's why this is not equal to this factor. So this is the thing when you want to do a collaboration of amplitude scaling, time shifting and time scaling. Okay, so this is done. The other operation that we have here is the fifth one, which you can say is time reversal. This is also very important. In this situation, what happens is, you want to reverse the time signal xt, and this is obtained by using gt equal to x of minus t. So what you do is, you flip around the signal. That is, what is there in the x time, where what is there on time t will be the same in time t equal to minus t on gt signal. So specifically what we are trying to say is that any event t1 which is occurring in xt, and that we are calling as x of t1, it will occur at time t equal to minus t1 in gt. So if you observe that, if you put this t equal to minus t1 here, then this will become x of positive t1. So by seeing this figure, you can say that whatever value that you are getting at positive t1 will happen at minus of t1. So you can see now from this figure that the signal is actually flipped around the vertical axis, and the signal that you obtain by doing this flipping is actually x of minus t. So there are many variants that you can apply on this flipped signal, and the variants are like, you can do shifting by a value of t naught or by a value of t minus t naught. So all these shiftings and scalings can also be applied on these flipped signals, which you have to exercise, and maybe you can see it on in your tutorial sheets also, these questions. So these are the variants that you can apply on these flipped signals. Okay, so if you have any questions related to all these basic elementary signal operations, you can ask. Otherwise, then we will move forward to the next topic. Okay, so the basic building blocks that we will be discussing in continuous time signal are, the following. So these are called as basic building blocks because some way or the other they will be used every time in continuous time signals, and most of the complex signals or the theory that you will build up will be on these basic basic functions that we will be discussing now. So the first one in this category is very important. It's a unit impulse function. This is the very basic and a fundamental function that you will see quite frequently in this course. So how it is defined? It's defined by delta t, and this delta t is defined in this following format. That is, if time t is not equal to 0, if time t is not equal to 0, the value is 0, and if time t is equal to 0, then it is undefined here. That is important. That is, delta t is undefined if time t is equal to 0. But at time t not equal to 0, its value is 0. And the other thing that is also involved along with this delta t is, that is, if you integrate this function from minus infinity to infinity, if you integrate this value, your value will come out to be 1. This is important. So if you plot this particular function on the time axis, it will look like this here. So you can see here that at time t equal to 0, at this point where time t is equal to 0, its value is undefined, and it is given by this particular vertical line with a arrow here. And note that the value that is given over here, which is 1, is actually the value of the area of this area of this unit impulse function. It's an area. It's not the magnitude. This has to be kept in mind. It's a area and not the magnitude of the impulse function. And rest of the times you can see its value is 0. So this is basically a unit impulse function, which is very important. You have to understand it because it will be used continuously in the signals and systems. So this is the definition. Then we have some variants which are available for this unit impulse function, and the variants that you will see here are given this side. So you can see you will have a shifted and scaled version of the impulse function, which can be defined as this. This is the shifted and the scaled version um, of the impulse function. You can see you are scaling by a factor a and then shifting by time t equal to t1. Again, you can apply the definition of the delta function here, and what it says is that time t not equal to t1, its value is 0, and for t equal to t1, its value is undefined. So it is not defined if time t is equal to t1. Again, if you integrate it between the limits of minus infinity to infinity, the value will come out to be a. So now the only difference is that your unit impulse, which was earlier here, is shifted to time t equal to t1, and now the area is a. Earlier it was 1. So this is a shifted and scale version of the impulse function, which is defined like this. Next important thing that I will discuss is that this integration limits, that is from minus infinity to infinity. So we can discuss something about this. Note that the integration limits do not need to be infinite. So we do not, it's not important that this infinity and minus infinity should be always there. It can be some definite limits also. So what I am saying here is that any set of integration limits that include the impulse function would produce the same result. So what it says is, it's not important that you integrate from minus infinity to infinity. You can integrate from this range to this range also. You can integrate from this range to this range also. But the important thing is, when you integrate between these two ranges, the impulse function should lie within this range. That is important. So if the impulse function lies within the, if you integrate in this range, your impulse function is lying here, then also you will have this same definition hold. But if your range is like this, then you can see your impulse function is not there in between these two ranges. Then this particular this particular thing will not hold, this one. So on the basis of that, what you can do is, with any time increment, delta t, you can write something like this. You can write it like this for the first variant, for the first definition that we have included here. If you see this one, so any delta t will work. So if your delta t is this one, minus delta t to plus delta t, so you can see your impulse is lying within this limit, then its value is 1. But if your delta t and minus delta, if your integral is something like this here, like some delta t1 this side and delta t2 this side, here there is no impulse lying within this integral, so its value will be 0. Same goes with this. So you have a, you have something t1, because this time t1 is here. So this time t1 is the shifted value. So if you take minus delta t and plus delta t around this t1, then you will get the value of a. So here if you take t1 plus delta t and then t1 minus delta t, then you have this impulse lying within this limit. So you can have this value as a. So this is also important, that there is no point in, it's not always necessary that you will have always minus infinity to infinity. You can have these limits also. Any questions here related to this? Okay. So the important question that we want to ask is that how can a function that has a zero amplitude everywhere except at one point having a non-zero area under it? So it's a very, you know, it's very difficult to visualize that how can it be possible that a function is having a zero amplitude everywhere, and except at the point where we have, at one point where the zeroth location you have a non-zero area. So to visualize this, to visualize this impulse function, what you can do is you can think in this way. So let us define this qt. Qt is a pulse function. Let us define it in a way that, for mod t between a by 2, that is in between these range of minus a by 2 to plus a by 2, what you have is you have a value of 1 by a. So the amplitude of this pulse is 1 by a, and for the rest of the points its value is 0. So all the other values are 0 for mod t. So what happens now is, if you try to reduce the value of a, so if you reduce the value of a, then what will happen? If you reduce the value of a, the width of this pulse will reduce, whereas the height of the pulse will increase. Why it will increase? Because the amplitude of this pulse is 1 by a, whereas the time duration of the pulse is a. So as you reduce the time, as you reduce the pulse width, the amplitude width will increase correspondingly. And when a tends to 0, like when a tends to 0, what will happen? It will give you a impulse type of situation. So now, and note that the area is 1 here. So if you multiply the area for this particular pulse, it is 1 by a times a, and its value is 1. So that is actually reflected here. So now you can see, as a tends to 0, the amplitude becomes infinite and a also becomes exactly 0. So this is giving you a hypothetical, explanation of how, you can visualize the impulse from this pulse situation.
Hello, sir.
Yes.
Sir, this meaning that when e tends to 0, the y quantity at x equal to 0 would be infinite.
Y at what you are saying? Can you come again?
The y quantity at x equal to 0 will be
Yes,
infinite.
yes, yes. It will be infinite because as you tends a to, that's why the amplitude is basically, it will have, its amplitude is infinite here. Yeah. So it's like a, it's a very generalized function which is very difficult to, setting is very difficult because here you'll have an infinite amplitude with zero width, and the area is one actually. That is most important here. Okay, so there are two properties of this impulse which are important. The first property is called as sampling property. In the sampling property, what you do is when you multiply the shifted impulse with ft, then what you will get is f at this time t1. So whatever value that you have shifted by, that will appear in this function f of t1. So it will give you this as the answer. So if you see graphically, then what is happening? It is very simple. That is, you have a function f of t which is given over here on the top, and what is happening here on the on the bottom, you have a impulse at time t equal to 1. So obviously when you multiply the two together, then this impulse is 0 everywhere else except at this single point. So what happens is this impulse will get multiplied with this value at time t1. So what you will get is f of t1 impulse at time t1. So it's as simple as that. You can see visually that how f of t times delta t minus t1 is giving you f of t1. So the important thing here is when you multiply the impulse with the complete function, then you will get one instant of that function out. So like at time t equal to t1, you will have one value. So that value will come out and it will be in the form of impulse whose area is f of t1. So this is basically a sampling property which we have here, and the other one is shifting property. By shifting property, what it means is if you integrate f of t delta t minus t1 dt for all the values of from minus infinity to infinity, then what you will get is f of t1. So we will see how we can get this shifting property. We will prove it. What you are saying is you are integrating this thing. You are integrating this factor from minus infinity to infinity, and what you are saying is its value will come out to be f of t1. So if you want to prove this, then it's very simple. What you can do is just before going there to prove this shifting property, let me give you a further some details about this impulse function. So definition of the impulse function is not rigorous mathematically. Actually, it's not the mathematical rigorous function due to the following reasons. Actually, it's not a actual function that we normally find in mathematics. So the reasons are that impulse function is not a unique function, because if you use this function, that is delta t plus derivative of the delta t, then what you will see is it will also satisfy the definition. It will also satisfy this definition which we have here, which we have defined for the impulse function. It will also satisfy these definitions. So it's basically, it's not a unique function that defines that will, it will not satisfy that definition. And the second is that it is not a true function in ordinary sense. By ordinary sense means that a ordinary function which you normally observe in mathematics is specified by its value for all time t. So for all time t, your ordinary functions will be defined, but this is not defined like that. So that is why unit impulse are also called as generalized functions. They are called as generalized functions, and generalized functions are basically defined by its effect on the other functions instead of by its value at every instant of time. So basically generalized functions are defined by their impact on the another function when you operate these functions on other functions. but they will not be defined by, but instead of their own values, instead of giving priority to their own values, they are actually defined as their impact on the other functions. So sampling property that we have discussed right now is actually showing you that here, you are actually seeing its impact on f of t. You are not seeing this function as an individual. So normally what we observe is we observe the impact of these type of functions on ft. So they are called as generalized functions. They are not typical functions that you observe in real life. So now what we will do is we will discuss how we will derive this particular shifting property. So it's a very easy way of doing it. So what you do is you actually you write like this. This is the equation that we want to prove. So instead of this integral, what you do, you put this one, the sampling one. As you know that this particular thing is equal to this. So what you can do is now you can put this here. So once you do that, and you know that this particular thing is independent of time t, so it will come out. And now you are integrating between minus infinity to infinity. Sorry, this will not be there. So now you will be integrating from minus infinity to infinity delta t minus t1. So you already know that this value will turn out to be 1. So you can easily prove that your f of, if you integrate f of t delta t minus t1, then the value will come out to be f of t1. And note that this will be a value at time t1 for this function f. It's not an impulse now. This is also important. This is a value of a function at time t1, and the impulse characteristic is gone because you have integrated the value from minus infinity to infinity. So this has to be kept in mind. Okay. So the limits again for this integration need not to be infinite, which we have discussed here. That is minus infinity to infinity. These limits again need not to be infinite. It can be anything between t minus delta t to t plus delta t. Can be anything like this. But one thing to note is that within these limits, you have to have this delta to lie within these limits. If delta is outside, then this value will be 0. Okay, so this finishes off with the basic concept of impulse function. The second one that we will discuss is unit step function. So unit step functions are useful in the situation where you want to model a signal which can be turned off or on at a specific interval of time. So if you want to turn on the signal or turn off the signal at a specific instant of time, you can use unit step functions for that. So the unit step function is basically defined like this, where you have ut given as 1 for t greater than 0 and 0 for t less than 0. So this is the definition of unit step function, and it can be represented like this. In some books, it is also written that at t equal to half, you have at t equal to half, you will have a value of half. So sorry, at t equal to 0, you will have a value of half. So that is, they assume it to be 1 by 2 here at the middle at t equal to 0. So this is the definition of unit step, and this yellow curve which we have drawn here is unit ut. So this is a unit step which is 0 before time t equal to 0, and it becomes 1 after time t equal to 0. A shifted version of the unit step can be written as this. So here you see you have shifted the unit step by amount of t1. So it will look like this, where the time is shifted and this particular thing has moved from 0 to t1. So one example that we can show you here is that if you have a sine signal which is running throughout the time, it's continuously running, and you want to if you want to turn on at a specific interval of time t1, and you do not want it to turn for the whole time interval as it is here. You can see the sine is continuously running from minus infinity to infinity. So what you can do is you can apply a unit step which is completely off till time t1, and then it becomes on at time t greater than t1. So when you multiply these two signals together, what you will get is this signal, and this signal is basically on after a specific time interval t1, and it is 0 before that. So in situations where you want to turn on a signal after a specific time interval t1, you can apply this type of function on these signals. Need not to be sine, it can be any signal. And similarly, if you want to turn off a signal after a specific interval time t1, then you can operate with this signal, which is actually the flipped around signal plus t1. So there is a time reversal here followed by a time shifting. So you can see that the signal will become like this, and this signal actually is when multiplied with this particular signal, which is running throughout from minus infinity to infinity, it becomes 0 at time t equal to t1. So it turns off. So this way you can see how signals are turned on and turned off if you operated with these type of unit step functions. So their use is in some way or the other in control systems, so you can make use of it like that way. Okay, so another important thing that we will discuss is the relationship between the unit step and the unit impulse function. So if you observe that unit step is basically related to unit impulse function with this factor of integration. So what you do is you integrate between minus infinity to t the impulse function here, and then what results that you will get is unit step ut. So if you see here, there is nothing fancy about it. If you observe that if the limits of the integration are from minus infinity to t, and if the value of t which you are seeing here is less than 0, I told you already that if the limit of the integration t is less than 0, and it's so the impulse is not lying in this area. So if the impulse is not lying in this area, then the value returned by that will be 0. And if the impulse is lying within this area where you are integrating, that is from minus infinity to t, the impulse is lying within this area, then you can see that ut will become the value will become 1. So the value of the integration, as you can see, it is 0 if the t is less than 0, and if t becomes greater than 0, then the value becomes equal to 1. So you can write it like this. By seeing these figures, you can write that there is a function fx which is actually 0 when this particular t is less than 0, because you have observed that this integral here is less than 0, and this delta function is not lying within this integration limits, so the value is 0 here. And if t is greater than 0, the integral which is represented over here includes impulse function, so its value is 1. So now you can say that this function resembles ut, because ut is also, if you see by the definition, it is less than for t less than 0 its value is 0, and for t greater than 0 its value is 1. So then this function fx, the integral that you have evaluated, becomes equal to ut. So now you can observe from this that integrals, that is unit step and delta function, that is the unit impulse, are related by a integral. Other way around is like, if you want to get the delta function out of the unit step, then it's a derivative operation. And this is quite simple, because if one is integral, the other one can be obtained by taking the differentiation. So this is given over here. This is just showing you, like, if you have a pulse which is given like this, and if you integrate this pulse, what you will get is this one. So within the integration, it will be like this. And the important thing is, when you reduce the value of a, as we have discussed earlier also, when you reduce the value of a, then this horizontal dimension will reduce, the vertical dimension will increase. So it will become an impulse when your a tends to 0, whereas how this particular function will become a unit step as your a tends to 0, because as a tends to 0 this dimension will reduce and this function will become like this. So this also shows you, like, how a pulse can become a unit step if you reduce the value of a. Okay, so another function that is important is unit pulse function. A unit pulse function is basically defined as pi of t. So if you define with a variable pi here, then this is basically defining a unit pulse function, and it is basically defined as that for mod t less than half, that is within minus 1 by 2 and 1 by 2, its value is 1. At t equal to half, its value is half. That is, you say that these values are half here, and then for t greater than half, that is mod of t greater than half means these ranges here, its value is 0. A generalized function with the variable tau here, see earlier we had a fixed value of 0.5, so we are keeping it variable here. So now we will have a variable parameter tau along with this. Now it's minus tau by 2, tau by 2 to tau by 2, and then we have 1 here. So in this situation, what will happen? In this situation, the function will become like this. Here you have for mod of tau less than tau by 2, your value is 1. Everything is same, but the only thing is the scaling factor here becomes tau, and these things will change here. Yes,
Hello, sir. Won't the middle, like the 1 by 2 will be mod t is equal to 1 by 2?
the middle one.
Yeah, sir. Because it is on the
Yeah,
both
yeah,
side.
yeah. Right, right. So it is also on the both side, right? So this will also be, a mod here. Yeah, right. So it will be 1 by 2 on both the sides. So it will also be this. Good. So this is a generalized expression for pulse functions. Now, the important thing is that unit pulse function can also be expressed as time shifted unit steps. So now you observe that the why we were calling it as a basic building blocks, though this particular pulse is a you can use it as a basic building block, this one, but again this can be again boiled down to the fundamental basic building block, which is the unit step. So you can observe now how this unit step, which is the basic building block, will help us in building the pulse function. Pulse functions can also be used as a basic building block, but more fundamental basic building blocks are unit step functions, because they are the ones from where you can build the other complex functions. So pulse pi t can be created by using this operation, which is ut plus half minus ut minus half. So let us see how you can do that. So if you take the unit step ut, if you take the unit step ut and if you increment it by half, that is 0.5, then what result you will get? You will get a shifted pulse to the left side, as you can see over here. So it is shifted by a value of minus 0.5 to the left. So this is the one which you will have when you apply ut plus half. And when you apply ut minus half, what will happen? It will be shifted to the right side. This we have already discussed in the definitions of the time shifting operation. So by using ut minus half, you are shifting the ut pulse towards the right by 0.5. So now if you add these two together, or sorry, if you subtract these two together, then what will happen? You can see here that for this value there is no value here, so then you will have 1 directly, this thing, and after this again if you go up till this value, there is no value in the minus side, so you will again get this factor here, but after this its value becomes 0, because after this range this and this gets subtracted out. So you can easily see that if you add these two, if you subtract these two, you will get this pulse function pi t. The value is given by this. So now you can see how unit steps can be used to develop pulse function. again, if you want to go and see the further insights in terms of the integrals, so here you can see how unit steps can be formed by using the impulse functions. So what we are doing now is we are just putting up the definition in terms of the impulse functions here, which we have already defined that unit step is integrally related to delta. So you can apply this definition here. So once you apply for this, you will get this, that is you are integrating from minus infinity to t plus half, and for here what you are doing, you are integrating from minus infinity to t minus half. You are just putting these values. If you see the definition, you can easily get it. So now what you observe is even the delta functions are the fundamental building blocks which you can help you to build, which can help you to get to this pi t. So if you subtract this integral from this integral, you will get it from t minus half to t plus half. So the important thing note here is that these two integrals should actually incorporate this delta function. If delta function is outside these two integrals, its value will be 0 as it is given over here, and its value is 1 only if t plus half, that is this particular integral, is greater than 0 and this particular integral is less than 0. And the reason why we are taking it as 0 is because your delta function is right now at 0. If it is a shifted impulse, then you have to change these limits which are given over here. So if you observe this definition carefully, you can visualize that if you can write this particular thing as mod of t less than half, and then 1 and 0. So now you can observe that if you do integration of the delta impulse within this range, then you got some function fx which we do not know that what that function is, but then we observed that this function, which is actually the integral of this, is resembling the pi t. So you can see that if you do this, if you do the integration of this, you will somehow or the other will get pi t. So this is another way of deriving pi t from impulse functions, and this one was the example of deriving pi t from unit step. Okay, so another function that we have is unit ramp functions. So these unit ramp functions are defined like this. It's very simple. That is, for t greater than or equal to 0, you have a value of t, and for t less than 0, you will have a value of 0. So it is it can be shown onto the right side where you have a yellow line which actually defines the ramp function, and it should be 0 here. So it's like this. So this is basically a ramp function, and the alternative definition of this, like this is the first definition that you have for the ramp function. The alternative definition of this can be that your gt, if you take a gt signal which is which is t, that is if you take this signal and if you multiply that with the unit step, you will get the ramp function. So again you can see that ut is acting as a fundamental building block for developing the ramp function. So this is shown pictorially here. So you can see if you do a multiplication of this signal with this unit step here, then what you will get is a ramp function which is given over here. Okay, so once this is done, this is the definition of the ramp function. So once this is done, what we can now see is the relationship between the ramp function and the unit step function. Again, like the way we have discussed earlier, ramp functions are basically related to unit step by integration. So you can see now here that if you integrate the unit step function between minus infinity to t, you will get the ramp function. And again, here also I'm showing you the same thing. That is, if your integration limits, that is from minus infinity to t, if it is lying outside this unit step, your value comes out to be 0. But if your integration limits enclose the unit step, then your value will come out to be t. because you will integrate this portion will give you this thing. So if you observe carefully, again these integral values, this particular integral value is giving a value of t when t is greater than 0, that is your integration limit is greater than 0. This integral is becoming equal to t, and for t less than 0, which do not include this unit step, its value comes out to be 0. So this integral evaluation is some way or the other relates to ramp function definition. That's why I have written it as RT, for RT equal to 0 for t less than 0 and RT equal to t for t greater than 0. So when you evaluate this integral, it resembles ramp function. So that's why we wrote it like this. And if you want to see pictorially, you can see something like this, where when your t, that is the integration limit, is changing from -1 to +1 to +3 to +5, then you can see how the area is evaluated when you integrate the unit step. So when your t is -1, there is no integration area involved here. But when your t becomes equal to 1, your integration area is is this one, for which you get a value which is here. When t equal to 3, a larger integration area is available, so that's why you will have a larger value here. And same and similarly for t equal to 5. So you can see that as the integration area increases, as you increase the time limits of the integration, you will get, if you join these lines, you will get a ramp function. Okay. The last one, that I think this is the last one that we have, is a unit triangle function. It is basically represented by this. So it's represented by this symbol, and it is defined as that for t between -1 and 0, its value is t plus 1, and for t between 0 and 1, its value is minus t plus 1. So this particular thing is basically this, and this particular line segment is actually this. And for the rest of the values, it is 0, which is this one and this one. So this is a definition of the unit triangle function. So the important thing that I pose to you, actually, I'll give you this as an exercise. You can do it at home, and we can discuss it next time. That is how your unit triangle. This unit triangle is there, right? So we want to express this unit triangle in terms of the shifted and scaled unit ramp functions. So you have to you do this exercise at home, and in the next lecture, what we will do is we will discuss how we can write this triangle function as unit ramp functions. So this you have to do, and in the next lecture, what we will do is we will discuss this. So if you have any questions related to all these definitions, because these are all elementary things, so if you still have any doubts related to that, you can ask. Otherwise, we will close this session today.
Sir, I have one doubt.
Yes. Yes.
Sir, in the unit impulse function, or sorry,
Yes.
unit pulse function,
Unit pulse. Okay.
sir, when we do this integration thing, like now the down, niche, niche.
Yeah.
Uh,
Okay. Okay.
Sir, here we are establishing 1 and 0. So, in the definition, we had the value of 1 by 2. So, sir,
See
we are
that,
not getting.
yeah, that one actually, it's a controversial situation, because if you see this thing here, if you see, this is actually, a discontinuity here. So that value actually, normally people do not, some books will define that zero point 0.5 at this discontinuous values, at this discontinuous situation, but normally it really doesn't, we don't care about these values. This is just for for our simplicity. Some of the books you will see, they will keep it as a value of zero point 0.5, but practically if you try to work with these signals, you really don't care that at this value you have a half or not, because what the most thing that you care is like whether you can able to make another signal 0 or 1. This is like the example that I have given you earlier here. You don't care that what value here you have is zero point 0.5, because you are interested in either turning on the signal like this at time t1, or turning off the signal at this at time t1. You do not want, you are not focusing on this thing, like that at discontinuous you have a value of zero point 0.5. That is really don't, we do not care about it. Okay.